All right, so yesterday we started our 1B.9 through 10 section. And so the main thing here that I wanted to make sure we understood how to identify a vertical asymptote algebraically and graphically, how to identify a hole algebraically and graphically, and then also to be able to understand the different and limit notations for a vertical asymptote and limit notation for a horizontal asymptote. Make sense? Okay, those were our goals for yesterday. Now we're going to keep going. Okay. Yeah. Where are we at? Is this right? Okay. Here we go. Yeah. All right. In rational functions, remember that the zero the denominator and not a zero the numerator. That's our vertical asymptote, correct? Now, the zeros in the numerator are what again? What do our numerator zero tell us? They're our x-intercepts, okay? The numerator tells us our x-intercept. The denominator tells us our discontinuity, our vertical asymptotes, right? So that's where we're going to keep going. Now, the graph of a rational function will never, ever, ever cross a vertical asymptote. Okay, it will never cross a vertical asymptote. Got it? Just make sure we understand that. So we're gonna look here, and so when we look at these functions, we're going to analyze what's happening. Notice that sometimes you have repeated factors, right? And so if you look at h of x has x minus 4 squared times x minus 5 divided by x minus 4 times x minus 5 squared. So do you see how some of my functions, my factors are repeated? Yes? So even after I go through and eliminate, I'm still going to be left with these values, correct? So let's talk about what that looks like. So when I go in here, I have a factor that eliminates. Agree? Okay. I have a factor. So what I'm left with after I simplify h of x equals, I'm left with x minus 4 over x minus 5. Okay. Because I'm still left with that x minus 5, that means that it's not a hole. It's actually still a vertical asymptote. Does that make sense? Okay. Because it did not go away completely. I'm still going to have a vertical asymptote at x equals 5. Okay. Make sense? All right. So let's do another one. So on f of x, so when we look at f of x, what happens to the x plus 2 squareds? They both go away, right? Because their degree is the same, right? Okay. X minus 3, what happens? They both go away. Now, what happens to x plus 4 to the 6 and x plus 4 squared? The denominator cancels completely. And what happens to it becomes a power of 4, right? I'm still going to have 4 of x plus 4 in the numerator. Okay. So what this means is that All right, guys. So before the announcements, we were kind of interrupted. So there's no vertical asymptote because there's nothing remaining in the denominator. Does that make sense? There's nothing remaining in my denominator, so there's no vertical asymptote. However, there are holes, and there are holes because I eliminated all the factors in my denominator. Yes? Okay? And those holes are saying that if I was to plug these values back into the original, it would be undefined, which is why they are holes. Got it? So there's holes in my denominator at every factor that was eliminated. And my factors that were eliminated were x plus 2 squared, right? Which means that this would have to be negative 2. X minus 3, which means that this would have to be positive 3. And at x plus 4, which means that this would have to be negative 4.
So only
the factors in the denominator. The denominator determines your discontinuity. Discontinuities are holes and asymptotes, right? All right.
But if it's not canceled in the denominator, then it's not.
If it's not canceled in the denominator, it's an asymptote, not a hole. Exactly. All right. So to make sure that we have that understanding, quickly do g of x. So you do g of x. All right. So let's talk about it. So on this one, on g of x, you have a x plus 3 squared and an x plus 3. So the one in the denominator goes completely away, but however, the one in the numerator does not. Okay. This means that it's not a hole. It's not a hole, and that just tells you that negative 3 is not a vertical asymptote. Okay. So our what we're left with would be x minus 6, x plus 3 to the 1, all over x times x minus 1. What's left in my denominator is going to tell me what type of discontinuity I have or what's not left. In my denominator, I'm left with 2 factors, which means that I still have 2 vertical asymptotes. One vertical asymptote is at x equals 0, and the other should have been at x equals 1. X equals 0 is because of x right here, right? The x by itself. If that becomes 0, it would make the entire denominator 0, correct? If I plug in 1, it's going to make the entire denominator 0, which is why there's a vertical asymptote at x equals 0 and at x equals 1. Because in the denominator, it was completely canceled out, right? Oh, you're right. There is a hole. Where's my pen? I'm trying. Yes. Sorry. There is a hole at negative 3. There is a hole at, because we canceled out on the denominator. Lo siento. No. Wait, hold on. I'm confusing myself. Yes. All right. Sorry for that. So yes, confirming. I don't know why my notes don't have that it's a hole. What's the purpose of taking notes before teaching? So that you don't make mistakes while teaching. And then what do I go and do? Make a mistake. And my hole is at x equals. There we go. Do I have them all listed now? Yes. Okay. All right. So at the bottom, what you're going to do is you're going to write your way of remembering what's happening. So it says, without simplifying, how can you tell which factors will create a vertical asymptote? So this is you summarizing what you learned. Does that make sense? It's because if you can summarize it, then you got it. And then you're going to share with your table what you wrote and how you're going to remember when are you going to have a vertical asymptote. So a little guidance is to tell yourself, how do you know if you have a vertical asymptote? How do you know if you have a hole? There we go. Okay, so telling yourself how you're going to remember, and that is what you're doing. If you can put it in your own words, if you need some help on remembering, maybe it would be the value remaining, the factor remaining in the denominator, or factor eliminated, or whatever you need to do, give yourself hints. How do you know? Are there no more events?
So if it was where it is a whole, it's x on the side, so it's x plus 3, so the whole would be at negative. And then the other one, it's x minus 4, so the whole would be at positive 4.
So at least one person at each table, make sure you hear how you're going to remember, whether it's a vertical, asymptote, or a whole. I think I know.
I just minutes and not and then you summarize it by rewriting. And then there's that was.
Oh, like it's left over. Yeah. All right. I don't even do it equals 0. It's just automatic.
Don't like the mark. Make a mark for it. I'm gonna get rid of this because make the mark for it. Make a mark for it.
Please ignore that conversation in the background. Yes. All right. So everyone wrote something? All right. Perfect. These were mine. So mine, how I just always remembered, is the vertical asymptote denominator factor doesn't cancel, right? So after I eliminate, it's still remaining in my denominator, then it's a vertical asymptote, okay? The whole, the factor disappears completely, which means it's gone, it's vanished, right? Those are just my words to help my brain. What your words are, your words. Does that make sense? All right. So, testing what you wrote down. We're gonna do a couple things. You're gonna do it quickly, quietly. So the first two, they're already factored for you. The second two, you have to factor and then do it. Okay? Yes? Okay. So quickly, based on what you wrote down, you would do, you're gonna test what you wrote down and you're going to find the discontinuities. So whether it's an asymptote or a whole, and go. Okay, on A, what do I have? What is x equal 3? I have a vertical asymptote at x equals 3. Do I have a whole?
Yes.
Where's my whole at? At x equals 4. Okay. On B, do I have a vertical asymptote? Where is it? X equals -3. Do I have a whole? Where is it? What kind of one? Positive one. All right. On C, do I have a vertical asymptote? At x equals 0. Good job. That's an at sign. I promise it was. I'm just going to write.
Oh.
There you go. That will make that 0, right? So your vertical asymptote would strictly only be because of the x, not because of x squared plus 5. X squared plus 5 will never equal 0. Does that make sense? Because every time I put in a negative, it's going to become a positive, right? So it would never become. So the only thing that defines my vertical asymptote is at x, okay? And then because nothing eliminates, there is no holes, right? Okay, on D, your factored form, this was a difference of 2 squares. So it should become x minus 3 times x plus 3. And then in the bottom, you should have had x plus 3 and x minus 2. That's what your factored form should have been. Using difference of 2 squares and simple factoring. What multiplied to give you -6, but adds to give you 1. So with that being said, where's my vertical asymptote? If there is one. At positive what? Positive. My vertical asymptote is at x equals 2. Because that's what will be left in the denominator, right? Yes. It's a this?
Yeah.
It's a 2? I thought it was a fairly noticeable 2. Yeah. But also you could have just did the math. What multiplies to give me -6 and adds to give me 1. Trust your math. Well, I wrote 2. I said it. All right. And then your whole would be at -3 because that would have eliminated from the numerator and denominator. All right. So hopefully we have that down. I know. That was a Fox response. All right. Moving on. Okay, here we go. So moving on, we're going to be talking about limit notations and being able to write and describe what's taking place with a function using limits. Okay, so here we have x minus 1 divided by x squared plus 2x plus 1. Okay, so when I have this function, I can analyze it from just looking at it and say, okay, well, what multiplies to give me this? What right? And so it's asking what values of x makes the denominator 0. So what values of x would make my denominator equal to 0? Well, I have x squared plus 2x plus 1. So essentially, I'm asking what would make, in factored form, what would make this equal to 0? So if we have x squared plus 2x plus 1, in factored form, what would that be? There we go. It would be x plus 1 times x plus 1, right? Because 1 times 1 is 1, but 1 plus 1 is 2. And that's how it's going to be satisfied. So what values of x makes the denominator equal to 0? Well, that would be x equals -1, right? I would plug that in and see what happens, okay? When this happens, notice that you have a double factor. What tends to happen when you have a double factor is that it's going to cause your left and right side, as they approach that asymptote, to go in the same direction. Does that make sense? So my left and my right are going to be approaching the asymptote and doing the same thing. So we're going to look at that from the graph so you can see what I mean. We know that we're going to have a vertical asymptote at -1. And I have a horizontal asymptote at y equals 0. Why do I know I have a horizontal asymptote at y equals 0? There we go. The degree of your numerator is less than the degree of your denominator, which automatically means you have a horizontal asymptote. Okay. So these are my discontinuities. Now it says we're gonna put in the calculator. We're gonna see what is happening around our discontinuity. So I'm gonna open the calculator, and I'm going to put in x minus 1, x plus 1. Okay, so do you see what I meant when I said when we have a double factor in our denominator, what ends up happening as they're approaching? They end up doing what? The same thing. Okay, another thing happened here. What do you notice happened on this side? Did it cross my horizontal asymptote? Yes, it crossed the horizontal asymptote. Your horizontal asymptote has errors, has room for error, room for change. It is not a permanent boundary line like a vertical asymptote. Okay, horizontal asymptote says, well, I would like for you not to go there. However, there are exceptions to the rules when it comes to horizontal asymptote, and that tends to happen when you have a multiplicity of an even number in your denominator. So notice this has a multiplicity of 2 on our x plus 1, right? If I have a multiplicity of 4 or 6 or 8, it tends to happen because it's not playing the rules of the negative. It's going to eventually, everything's going to end up getting squared, which means that I only have so many things that are below 0. Does that make sense? And so that's why that ends up happening. That's why I wanted us to look at this problem, because this is a unique example of when you will end up crossing the horizontal asymptote. Let's look at the table so you can see what I mean. So as the numbers keep getting bigger, they have clearly, after 2, we are surpassed the horizontal asymptote. Okay. And that's because we can't contain it being negative because I'm squaring it, right? And it's a square or a fourth power or sixth power is going to take a negative and turn it into a positive. So it's going to have to go above. Make sense? All right. So horizontal asymptotes have exceptions to their rules. Okay. The vertical asymptote is permanent. You're not crossing me. You're not getting by me. You can get as close to me as you want. But horizontal asymptote, because of how math works, there's a limit to it. On the negative side, though, that bad boy is going to stay under, right? I'm going. I'm just going to keep getting closer. But on the right side, when I start plugging in those powers, those x values greater than 2 or 2 or greater, that's when it's going to start happening. Okay. All right. Cool. So now what do you notice? Well, that's what you're supposed to talk about. So when we're talking about what do we notice, the main thing we want to focus on is that typically because of this is why they're going to just have you focus on the behavior as it's getting approaching your asymptote. What's happening here? Oh, I didn't go above enough. I need to be above my horizontal asymptote. It's not drawn to scale, pretend that it is. I did my very best. Okay, so as input values are coming, what do you notice about the graph around the values of x that make the denominator 0? Well, as your input values are approaching -1, the output values are doing what? They're decreasing without what? Bound. So as input values approach -1, the output values decrease without bound. Okay. And that's where we go into writing our limits. So when we want to represent this mathematically, instead of using all these words, we will start writing it in limit notations. Okay. So when I'm describing this, this is where this is coming into play. I will in a minute. So when you are reading it, and anytime you're reading it, then when you're writing the limit, that is what you should be creating. So because we said it's increasing or decreasing without bound, then we would write it as the limit as we go to -1 from the left. It's going to -infinity. As the limit as x goes to -1 from the right is going to -infinity. Okay, so that's where this comes into play in making sure that we are understanding and comfortable writing. So you can say it in words, but we need to be comfortable writing it in limit notation. Does that make sense? Okay, so we need to be able to go back and forth between the two. So here it is. So we have this function, and on this function, what time do we get out of here? Oh, fudge.